Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking a little bit more about current. This time we're going to be doing it in the context of Ohm's law and resistance. So I've given in some sense a microscopic view of current. I've defined what current is. As a reminder, current I is the flow rate of charges. Another thing that you need is voltage drop or potential difference. That is represented by delta V. That is the energy per unit charge, or the work per unit charge being done within the circuit. And in the microscopic view of current, we can write something like the current density J is given by sigma times the electric field E. So E in some sense is going to be proportional to delta V divided by the distance over which the voltage drop is applied. J is basically defined as current per unit area, and then sigma again is the what's called conductivity of the material. And so this is sort of the microscopic view. So what we want here is the more macroscopic view. What do we actually measure within our system? And the answer to that is that we can measure voltage drops and we can measure current pretty well within a system. Of course, you need a voltmeter and an ammeter to do that. You hook up your voltmeter in parallel to the thing that you want to measure the voltage drop across. You hook up the ammeter in series and you get a current. The relationship that holds is that for many types of resistors of materials, if you were to increase the current that passes through the material and measure what the voltage drop is doing as you increase the current, you'd get this nice straight line plot. So the more current that passes through, the more the voltage drop is, and this is a linear relationship. The slope is called resistance, which is usually represented by a capital R. The unit for resistance is the ohm. And this is an example of what's called an ohmic resistor. So unit for resistance is ohms. We use a capital omega. This is for specifically what are called ohmic devices or ohmic materials. There are non-ohmic materials or devices such as diodes, in which you essentially have no current or very little current for a very wide variety of voltage drops, and then all of a sudden you get an exponential current once the polarization flips. But for ohmic materials, this is linear, and so the material obeys what's called Ohm's law. And so Ohm's law says that delta V across your device is the current passing through the device times the resistance of the device. And so these terms, the resistance does not depend upon voltage or current. So R is roughly constant when voltage or current is changed. And I will talk about that a little bit more in depth in a separate video. It essentially depends upon a term called resistivity, which is the reciprocal of conductivity. So resistivity rho is equal to 1 over the conductivity. And actually, it's usually the resistivity that we measure for ohmic materials anyway. Okay, so this basically means if I double the voltage for an ohmic device, I also double the current, and so the resistance stays the same. So this is another way of saying this is doubling voltage also or results in doubling current, and vice versa. So that R is unchanged. Now there is a little bit of an asterisk with this statement, which is that resistance is temperature dependent, and so as you run current or run voltage, really as you run current through a device for some time, the device tends to heat up, and so that does actually change the resistance, but that is a heating effect rather than just a current effect. It takes some amount of time to elapse for the device to have heated up, and once it reaches a certain temperature, it kind of stabilizes, and then you have a constant resistance, and even if you up the voltage or decrease the voltage, you get very small changes only in the resistance. Let's do a quick example. All right, so here's an example which asks how much current needs to pass through a 150 ohm resistor if it is to have a voltage drop of 90 volts. Now note that I've used the word here, voltage drop. This is, again, the same thing as a potential difference. And so this 90 volts is your delta V. This right here is your R. Delta V equals IR. That means that I is delta V over R. And so that is 90 volts divided by 150 ohms. And so that should come to 0.60 amps. And so that is how much current would need to flow through this device. The other part of this short lecture is power in ohmic devices, power use, and that kind of thing. So recall that power, often P is defined, P is how much work is delivered per unit time. And so that would be basically how much charge times how much voltage drop is the charge moved through divided by time. But remember that this Q over delta T is the same thing as current. So power is I delta V. Let's write that again. Power is I times delta V. So that is ohmic power. And in addition to ohmic power, in addition to this form of ohmic power, we can recall that Ohm's law says delta V is I times R. So if I substitute this delta V in for this delta V, then what I have is power is equal to I times IR. And so that gives me power is equal to I squared R. That is also a pretty useful equation. This is power loss is often denoted in these terms. Finally, I can rewrite this equation to say that I is delta V over R. And so Ohm's law, once again, can be written as P is equal to delta V over R times delta V. And so I can also write that power is delta V squared divided by R. So all three of these are valid equations. When do you use each one? Well, problem solving wise, you use the one that has the unknown on the left hand side and the knowns on the right hand side, which should be obvious. Conceptually, when you use it is very often there are questions like, if I double the resistance of this, let's say, light bulb, will it be brighter or darker, and how do you know? So think about that. If I were to double the resistance of a light bulb, would I expect it to be brighter, therefore taking more power, or less bright, therefore taking less power? You can pause the video while you think about the answer, and then start back up when you're ready to see how your answer compares to my answer. Okay, so if you have paused the video after this question, you may be, you could make an argument coherently for it goes up and it goes down depending on which of these equations you use. Typically, the light bulb is plugged into a power supply, let's say like a lamp, and that lamp is plugged into a wall outlet. And by being plugged into the wall outlet, one of the things that this implies is that you have a constant peak voltage that you're getting. And in fact, the lamp essentially converts the AC signal into a DC signal for you. So you have, in some sense, like a constant voltage. So if the voltage is constant and the resistance has doubled, then the equation that you'd want to use is this equation right here. And so constant, doubled, therefore power has fallen by a factor of 2. It'll be dimmer. And so this means, among other things, that if you take two light bulbs and plug them in series with each other, then they will be dimmer than one plugged in alone to the same power supply. Although we haven't really talked yet about series and parallel resistors. So let's do one last example. All right, so here's a two-parter. Let's consider a 60-watt light bulb connected to a 9-volt power supply. That is, it's 60 watts when drawing from a 9-volt source. So how much current does this light bulb draw, and what is its resistance? So as far as the current is concerned, power is I times delta V. That implies that I should be power divided by delta V. And so you have 60 watts divided by 9.0 volts. So 60 divided by 9 is basically 6.6 repeating, essentially. So we'll call this 6. Let's do two signifigs. We'll call it 6.7 amps of current. Okay, and what's the resistance? Well, P should look like delta V squared over R, and therefore the resistance R is the power. Is the delta V squared, the voltage drop squared divided by the power. So that's 9 volts squared divided by 60 watts. That comes to a little over 1 1/3 ohms. Actually, I think it comes to 1.35 ohms. So, and you could maybe round that to 1.4 if you wanted 2 sig figs. So that's it. That is a couple examples for the price of one examples for power, for ohmic power specifically, and that's it for today's little lesson on Ohm's law. So thanks for watching, and I hope you've learned something.